It's 2022's 18th week. This is Talkin Science. We're back diving into the latest in science and space. A meteorite that landed in Victoria in 1969 has shown to have the ingredients for life, adding to the evidence that those important building blocks crash-landed here millions of years ago. The James Webb Space Telescope passes its final alignment and tests. It's now ready to study the universe in the greatest detail yet. And NASA has announced a new mission to Uranus and Saturn's moon Enceladus are beginning to be drawn up, marking only the second time each will have been visited by us.
This is Trekzone's Talkin Science.
Or your monthly reminder that Trekzone membership is available via the join button under each video on YouTube or via the trek.zone/support. Plus Trekzone's on Twitter, Facebook, Instagram, and your favourite podcast feed. Find us, like, follow, and subscribe. Brad 2 on social media at btucker22 on Twitter. Dr. Brad Tucker on Facebook. Brad, welcome back. We've been treated to an awesome planetary alignment in the past week and a bit. Saturn, Mars, Venus, and Jupiter all participating from our vantage point.
Yeah, it's been a great view in the sky, and it's going to last for a bit of time. So now that Venus and Jupiter have kind of overpassed each other, we'll get those for, kind of until end of June. But right before we lose Venus in June, Mercury will join the party, so we'll actually have 5 planets in a row during that time, just for a short amount of time. So it's definitely a good time of the year to see what's being put in the skies, essentially, for us.
Very, very cool. Well, let's crack on with the show. It turns out the stuff of science fiction legend may just stay there, with Chilean researchers suggesting no benefit to hibernating humans for long-duration spaceflight because they compared hibernating bats to hibernating bears and found a similar metabolism. If that happens to humans as well, scenes like this from Star Trek are not going to happen.
Yeah, and look, there's a lot of talk and looking, obviously, at this. And I think this is quite an interesting study to do kind of a statistical look at all the animals that do hibernate, how they save energy, how they change their metabolism, and how they adapt to it. And it just appears that pretty much it doesn't seem efficient in the way it is. In fact, I think they say that sleeping probably would be better in terms of saving energy-wise than hibernating based on the way we make our makeup. So, it obviously doesn't mean that you can't do something else, but an interesting study in terms of any likelihood and the venues that may be likely for this to happen.
The mysterious gamma-ray burst coming from the centre of our galaxy, Brad, may actually be from a rapidly rotating neutron star, according to Associate Professor Roland Crocker there at the ANU.
Yeah, so this gamma-ray excess from the Milky Way center. So his master's student, Anuj, was looking at this. And what they're essentially saying is, well, we know things called millisecond pulsars. These are neutron stars that spin very rapidly, and they emit some gamma rays. So if we had a study and we understood the population of them, and so they modeled what is the likely population of these rapidly spinning neutron stars, and therefore how much gamma ray could they emit across the Milky Way, and it does seem to be that there is a similar value, that what we see coming out of the center of our galaxy matches what a bunch of these essentially can contribute in total. And so maybe indeed, now that we just know a bit more about the neutron stars, these pulsars, and where they exist in our Milky Way, maybe this excess is from this rather than something else. And this excess is quite important because we're trying to understand why it exists for models of dark matter, for models of matter and antimatter annihilation. So this understanding of where this extra gamma ray light essentially comes from in the Milky Way is quite important across a few different areas that people are trying to understand.
Well, a fresh examination of meteorites that landed in the US, Canada and Australia is firming the notion that they may have delivered the vital chemical ingredients for life early in planet Earth's history, Brad.
Yeah, look, this is always this big question of where did the ingredients for life come from? So when we say ingredients, we're talking about things, in this case, the nucleobases or the nitrogen bases. So these are the basic things that make up DNA and RNA. Now, DNA and RNA have five, well, DNA has four, but then RNA replaces one. And three have been found before. So we found kind of 3 out of 5 of these bases before, but the missing 2, C and T, have now been found essentially or reanalyzed and discovered in these meteorites. Now, there's other things that you need for DNA and life. You need sugars, you need amino acids, and some other proteins. But the fact that these key ingredients at least are that further step, and they're at least found in meteorites that have been crashed into Earth, is another big step into understanding just how life came to be on this planet.
And scientists previously had detected on these meteorites 3 of the 5 chemical components, as you're talking about. They're needed to form the DNA. Now, in the last week, they've announced that they found the other 2. After a bit of fine-tuning, we've talked about this before on Talkin Science, how you always will find new things in your research if you go back and have a look with a fresh set of eyes or even with a different way of finding things.
Yeah, and this with these meteorites, it was always realized that they were quite unique. They're what we call carbonous chondrite meteorites, and they've always just realized have been quite special. And so the Murchison meteorite has essentially been studied heaps of times. A few years ago, what we said was pre-solar grains, essentially ingredients that didn't come from our solar system, but another one that essentially 7 billion years old as opposed to the 4.6 of our solar system. And so you only take a little bit at a time and reanalyze it just to, as you said, with new techniques coming online or new different ways of looking, we can analyze it. And so it is good that they've been preserved and good that these other 2 parts of DNA that complete the pairs, essentially, they pair off. A goes with T and C goes with G. And so now that you kind of completed those pairs from the same meteorite, that's quite key, because it's one thing to say, this meteorite had a few, and maybe this had a few. Yes, okay, they still come from space. It's better, at least, if they come from the same object, because they're likely to come from the same groups of objects in the early solar system. That early bombardment of the Earth 4 billion years ago, when there was lots of asteroids and meteors raining down on the Earth, you want them from the same type of stuff, rather than kind of, oh, if you got this meteorite and this one and this one and this one, you just want it to be more common. And so finding it on the same meteorite is quite important.
And the research team examined material. We've talked about these meteorites in this story, but where did they come from? Well, one fell in 1950 near the town of Murray in the US state of Kentucky, one that fell in 1969 near the town of Murchison in Victoria, and one that fell in 2000 near Tagish Lake in Canada's British Columbia province. Such a vast area that has been covered and studied. Interesting that all 5 of these building blocks have been found in the one meteorite as well. That's not the only part of this story, though. They're the building blocks. It has to then jump into a warm, watery setting to form the living microbes that can reproduce.
Yeah, and this is, I think, the key. We're not saying problem solved, that's it. It's at least where the ingredients come from, right? I always say, I could be told what the recipe for baking is, but putting it together and making sure it comes out right is one thing. Throwing flour and sugar at something and hoping it turns out well is another. So it's one thing to say, yeah, they came down to Earth, great problem solved. Well, no, there's other things that had to come in the right environment, in the right circumstance, in the right way for these to happen. So, it's still a big question, but I think the other exciting thing about it is if you found them on meteorites landing to Earth, this also then always supports these ideas that Venus and Mars likely had these ingredients coming down on them as well. There's no special reason they landed on Earth. They would have landed on Mars. They would have also landed on Venus and Mercury to a certain extent. But when we think of Venus and Mars as being habitable, they too had this stuff coming down from. So either they also had life at least early days, or they didn't have the right situation for life to arise from that, which is very likely. So it definitely helps. And again, that understanding of the possibilities and evolution of other planets, not just Earth.
Well, the $10 billion successor to the Hubble Space Telescope is now fully focused and aligned, Brad, with light bouncing perfectly off its mirrors to form incredibly detailed imagery in all 4 of its instruments. We're going to see those in a second. Finally, a series of events that have gone off without a hitch for the team at the James Webb Space Telescope.
Yeah, look, obviously it was a long path to get it into space, but since it's been into space, they've been nailing them. And the key here is kind of seeing in this image is the telescope was folded, and all of those mirrors, when they were folded, were slightly off a position. So the segments had to be perfectly aligned. You know, we're talking about less than a micron or a micrometer precision. So, you know, way better than a nanometer a millimeter. So we're really talking about precisions that are on the scale of, you know, something that is ultra, ultra fine in order for the alignment to be perfect, in order for the focus to be perfect, and then in order for the light to come through the telescope and optimize it. Because you don't want to just put the telescope and then have the images slightly blurry. So it's been a process over the past couple of months to get all of those mirrors slowly into position. It's kind of a lot of, is one or two better? And then you move it, because obviously all of those little segments at Honeycomb can move independently. So you can't just say move this one into position and then move this one. They all have to move kind of in sequence and in syncing. But that is now, as you said, done. And now all of the light is focused and coming through those instruments on James Webb.
Now, one final calibration check on the data delivery side of things, which could take another couple of months. Agonising details, Brad, that are well worth checking off, but surely everyone is champing at the bit to get this one going.
Yeah, and look, and the last stage is actually the fairly normal stage, and what we mean by that is every new telescope or camera or instrument has to be calibrated. You know, has to perform. You know how it has to work. Even when you're taking your phone. And you take an image, you want your camera to focus right, and you got to make sure the lighting's there. These are all little things that the telescope has to do. We also have to do the base level calibrations to know that when we measure something, what it's measuring. So, but this is very standard and very kind of normal process. This is the normal process, we say, as part of commissioning. So the fact that all this really unique stuff that was just unique to James Webb and how it was built is done and working means it's a fairly, I wouldn't say straightforward and normal, but a fairly clear process that has been done lots of times, and we know how to solve when problems arise and how it works. A lot of these other things were such a first-time situation that it took a lot of debugging and work to make sure it could be solved. So definitely the home stretch here of the telescope. And they always wanted to be online by the end of June. That was the goal, 6 months roughly from launch being December 25th. They're on track for that. I think that's the exciting thing. They are on track for what they envision as a kind of a 6-month phase. And then the awesome science starts.
Yeah, absolutely. And looking forward to some of those images being relayed by our friends at the Tidbit Miller Tracking Station. Well, these are the images released by NASA. They're engineering samples, so they're not pretty. They're not designed to be pretty, but they are certainly showing off different views of the Large Magellanic Cloud. Something that we know, something that we've seen plenty of times before. We know what it should look like. Sizes and positions of the images here depicting the relative arrangement of each of Webb's instruments as they pick up the light coming from the telescope's golden mirrors, including that 6.5 metre wide primary reflector. They may not be intended to be exciting, Brad, but really they are, aren't they?
Well, they are, and especially because people have already comparing them to previous images, say from Spitzer or other infrared telescopes and things like that. And the clarity and improvement of the image is just dramatic. It's not even, comparable in terms of what you're seeing when we compare it to a previous image of these areas and what James Webb is seeing now, especially the MIRI image of one of the nebula parts of the Large Magellanic Cloud. You just see, you in previous images, we only actually see a few stars plus a little haze. Now we see the brighter stars very crisp plus all that background stuff. And so it's delivering exactly what we thought. We're not only seeing fainter objects, but we're seeing brighter objects in clearer and more detail. And that's always been the name of the game: better resolution and better sensitivity, how far we can see.
Well, from the butt of jokes to a mysterious moon orbiting Saturn, NASA's announced we're going to be learning a little bit more about the outer solar system in the decades ahead, Brad.
And this was part of the planetary science decadal plan. So in astronomy and in planetary science being just exploring our solar system, they kind of have a group of scientists come together that represents everyone, say, this is the priority that we think based on feedback from the community, what people want, what are the science questions, and then make a recommendation saying this is what needs to happen for the next decade. And in planetary science, they list what are going to be the two or few missions that should be focused on. Now, that doesn't mean that they're going to happen next decade, but they essentially start next decade. So obviously, we have new missions already in the works and flying. So they say now over the next decade, start to build these and design them and get to them their places. And as he said, two of the places are Enceladus, the moon of Saturn, and Uranus. And both have very good, interesting reasons why they're at the top of the list, but also why they haven't been explored previously, but now. And this is based on a lot of new understanding, a lot of new data, and a new insight into what we think we can gain from studying these places.
Well, unlike Jupiter and Saturn, Uranus has only had one visitor from Earth, a brief flyby by the Voyager 2 spacecraft in 1986. And ever since, astronomers have been lobbying for a dedicated mission. What curiosities does Uranus potentially hold, Brad?
Yeah, and I think it's important because the Voyager didn't even really orbit, right? We're not talking about other moons and planets that have missions that just orbited and spent years at it. Voyager literally just flew by, took a couple of images, and that was it. Uranus is exciting because Uranus and Neptune are what we call ice giants, for one. They are different than the gas giants of Jupiter and Saturn. You know, we've changed our understanding. Jupiter, Saturn, Uranus, and Neptune are not all the same. Uranus and Neptune are very different from Jupiter and Saturn. And they're actually quite common when we see them in other star systems, exoplanets. So that just gives us an understanding of this whole new type of planet that we're now appreciating is fundamentally different. The way the weather acts on Uranus and by extension Neptune, the composition, some of the moons, as you said. So there's a lot to understand because we just haven't studied it in detail, but we now see its bigger role. And look, to be fair, you know, Jupiter only had its first dedicated mission with Juno now, which is going on, you know, and that was a recommendation from 2 plans ago. So it's, you know, now the technology is changing. We can spend time on some of those outer, larger planets and places that we generally haven't had a chance to visit. You know, the current missions have all been focused on some of the moons, with missions planned to Europa in the works and Titan in the works, visits to asteroids. There's been a lot of that stuff that's been the focus. We had New Horizons that visited Pluto. So now there's a bit of time to focus on some of these other ones because people realize you can't just only focus one object. We have to kind of spread it around across all of them.
And how would you be as Uranus? You know, you watch another probe go past, the New Horizons spacecraft often goes to Pluto of all places. Pluto gets its own mission, not Uranus. But anyway, it's coming.
Look, it has been
soon.
the forgotten child and plus the laughed at child as well. And I think it is. I think we're also benefiting from just cheaper, quicker technology. We can build probes easier. They can do a lot more science. We can get better bang for our buck in terms of what the measurements are. So we're benefiting from that as well when it comes to exploring these places. You know, New Horizons wasn't that fancy, and in terms of it took 10 years to get to Pluto. It only did a flyby. So at least with Uranus, Voyager had imaged it. We hadn't had any images of Pluto, and it just kind of zipped past it. But it at least had some instruments on it, where the belief is with this Uranus probe, it will be able to do lots of different measurements like we've done in Jupiter and Saturn, and also explore some of the moons of Uranus in addition to just the planet itself.
Well, let's talk about Enceladus now, or Enceladus, the 6th largest moon of Saturn. Just like Uranus, it was discovered by William Herschel. And we didn't know much for 200 years after discovery until Voyager flew past in the 80s. And then Cassini in 2005 revealed a subsurface ocean and loads of ice.
Yeah, it was really the Cassini probe that pushed this into the realms of being very interesting. Again, we kind of knew Europa was interesting because it was bigger, easier to study. Same with Titan and Saturn. But Enceladus, because it was smaller and we had much data on it, there wasn't really much to learn. But when Cassini flew by it, and towards the end of the Cassini mission did some dedicated flybys with Enceladus, and we saw geysers essentially coming off of it. We saw things coming out of the surface, clearly a sign that there was water or liquid, at least with hydrogen and oxygen underneath the surface. meaning that underneath the surface it was temperate, i.e. not just frozen ice, but there was an ocean. Again, like with Europa, that we believe, and some of the other moons, it was really a game changer. And so it was kind of like, all right, well, we have to explore this one as well. This is just too interesting. And given the technology and knowledge and gain from the missions that will go to, say, Titan and Europa before this mission is flown, it is a good plan, because you can say, all right, we're going to fly to Titan with Dragonfly in 2027. We'll do the Europa Clipper as well. We can gain on what that knowledge is from those studies and build it into our study of Enceladus as well. So very exciting, very interesting, and kind of that very big step into exploring that big question, not just of the Jupiter and Saturn systems, but really these moons, which we think are very viable places for life.
Going to be very, very exciting, and we'll be learning about these discoveries, Titan, Europa, Enceladus, Uranus, all by the time I'm about 60, 65, which puts you at about 50, 55, doesn't it, Brad?
Something like that. It's a bit of a dedication, let's say, in order for these missions. But that's the thing, right? James Webb, as we were just talking about, took 25 years to build and get in there, There are some people that was just their career, one thing, so it is dedicated. These missions do take time, but I think the exciting thing is we are seeing more and more of them, right? It's not just we occasionally get a mission to Mars or somewhere else, or we just had Voyager. We're now planning multiple places in a batch. And this is also just the U.S., keeping in mind. This is just the U.S. decadal plan. Europe also will have its own priorities that it works around it and build own missions. Japan is doing it. So now as more countries build them, there is that greater cooperation and having more missions happening to different places. So, it's becoming quite busy to see them. So, the discoveries will not be, we just wait, 10 years for the next probe, but now every year there's a new mission reporting back new data on a new place in our solar system.
Cannot wait. Well, Brad, it is great to pick apart the stories of the past few weeks with you. We're going to do it all again next month. Thanks for coming in, mate.
Thanks.
Thank you.